Okay, so hello everyone. I guess since it's just Sunday today and my session got postponed, so it was, well, of course, because of Raksha Bandhan. So I'll just introduce myself and we'll start the session. I won't take it long for today's session. We'll discuss the assignment tab and we'll go through the lecture slides. Does someone want to say anything? Mukhtar Pichai?
Yeah, good evening, ma'am. And just I
Yeah,
need to
good.
say greeting. That's it. So I
Sorry?
think just I need to say good evening only. So it's
Okay.
the first time I'm attending the classes.
Oh, okay,
So
okay.
thank you. Please go.
Yeah. Um, yeah, so I'm Jagriti. I'm a PhD scholar at IIT Gandhinagar. I'm currently in my fourth year. I work in the medical ultrasound engineering lab with Professor Kala Markado Shekhar. So my work is on ultrasound tissue characterization with quantitative ultrasound. So I develop techniques so that I can see more into the tissue microstructure and differentiate in between types of tissues. So it's like a overview of it. I don't play with learning methods yet, but I have been working with physical learning methods. So that's how some glimpse of my thesis is all about. Okay, so we'll start today's session. So today we'll see week three. Like previous weeks, we won't go much into the detail, but I'll just show you quick through the lecture slides because this week I thought that there was more content which had to be like you should know more into it. It isn't just about the theory behind it, but there are also some formulas in it, some intuitive relationships that you should know. So till now we were looking about microscope, electron, optical. We looked at different types of microscopes, and then eventually what comes is nothing but the history of microscopes. So how it all began. So Zeiss or Zeiss, however you all pronounce it, they have on their website they have a very good flow chart for the same, that okay how it works and how different how the history of microscope went by. So if you see over here, the first compound microscope, simple microscope was just like this. And Carl Zeiss was the person, Zeiss was the person who did it. So the history has come upon that, okay, they did this kind of systems, tried metal ones, changed the source of illumination. Different people tried, then ultraviolet source, then they tried on bit of filter, that's fluorescence, and then eventually their first prototype of phase contrast microscope came through. After that, it took a lot of time for the electron microscope to come, but as we saw in the lecture slides, that here, the first ones, the Max Knoll and Ernest Ruska, they were like doing their PhDs, and while their PhDs, they just went on an idea that okay, let's just do something so that something, if my specimen is transparent enough, so I can have my beam to pass it through it, so it would directly go through it. And their first idea of that electron microscope was nothing but our Nanan Lonely transmission electron microscope. After that, Manfred and this Mr. Adrian, he went up his first idea that okay, if I have some opaque specimen, what should I do with it? So in 1938, they did that particular thing, and then later, this person from Cambridge saw that okay, this idea hasn't been commercialized and people are making their own for the purpose of their own imaging systems or for their own specimens. So that sample is very, the system is very small enough and it's not commercialized. So he wanted the idea to be amongst the community, and then he went up and then made it to the field, and finally 1965 that thing came upon. So here on Z's website, you'll be able to see that okay, how much different kinds of till date their newest systems have come through. and then how their optics have also evolved. So okay, how the physics changed and what kind of lens they took, how to prevent the effects of diffraction for the same, how different types of chromatic or achromatic, the spherical, those versions they saw through it, and eventually are different kinds of microscopy techniques. Okay. So with that, we know that okay, how a light microscope and an electron microscope works. If you just focus on these two diagrams right there in the corner, you see that for a light microscope, only thing that you need is a source so that it will illuminate the light on your specimen through the condenser lens, and through objective you will be able to focus this light onto your projector screen, that is through your to your eye, and you'll be able to see that. But in terms of this electron microscope, there comes two things. That whether how is like okay, you are sending electrons via this source of electrons. This source can be anything. For now, let's just assume the source is similar to how our conventional sources used to be. Then you have a beam of electrons, so you know that current travels from anode to cathode, and electron travels the reverse way, so cathode to anode. Now we have here two anodes in the way. First anode would be the one which will have a very few it's like the voltage for this would be very few because it's just the one where we'll be extracting electrons from it. And the second one would be where you are accelerating or the beam of electrons towards your specimen. So that one would be the one that will pass through. Now here comes two ways that okay, if your specimen is getting interacted, if the electron beam is getting interacted with your specimen, or is it passing through your specimen? So through that also the electrons which are generated are also different types. So we'll see that okay how that varies, but usually what we actually want to see over here is the way in which your electron beam is interacting with your specimen. Also, the way in which the electron beam is interacting with the rest of the components in your microscope. Okay. So in a way, if you see here, so this is nothing but the commercial system that you might have seen. It's so at IIT Gandhinagar we also have two of those. Those are from Joel. So these is like a that's is like in competition with Z's, but it's a Japanese manufacturer. So I guess that's also quite expensive enough that we have in our institute. We also charge people from around if they want to use that system. So if you cut through this maximum system, so in our institute, what the system I have seen is nothing but would only take one story floor of space. But here they have placed the system on this tabletop. So depending on the height below and the sources above, also if you have multiple detectors in between, your system will get huge and huge enough. Okay. So now different detectors are nothing but if you want to do different kind of imaging, or if you want to detect some of the characteristics that your sample specimen has, and if the electrons which will interact with your specimen would radiate in the similar manner. So that is why you need this different detector so that you can characterize your sample fully. Now, in this case, you have this X-ray detector. Then next thing that you have is nothing but here, this red ring that you see, it's also a different kind of detector. It's something that is used for annular diffraction. So that's a ring. Then you have this prisms or this EELS spectrometer. So there are different detectors. But if you just pass through, see this entire structure, what you see is that, okay, you have a condenser lens, you have a objective lens, you have your specimen in between, you have your projector lens, you have your eye or where you capture the image. On top of it, you have your source of emission. Now here in this case, source of emission can be a thermionic gun. Why a thermionic gun? I suppose you all know that okay, we heat a source so that it will generate electrons through it. We extract the electrons, and these lens, the aperture, all will allow us to focus it on our specimen. Later, we'll again retract the beam from it. Okay, so how the electrons are reflected back. Now, this is how the simple architect of it looks like. Now, if your sample is transparent enough, the system or how we image is nothing nothing but called as transmission electron microscope, and also the specimen for the same or the sample for the same would be small enough so that we our beam passes through it thoroughly and tells us the entire architecture of the sample that we are imaging through it. So you have the source, you have condenser lens, the aperture for the same, place your sample. So the ray diagram is much more simple. You just have a source, a condenser lens with an aperture, a specimen, and all of those things. Okay. So this is in basic that okay how you should know. And so only thing that you should know over here is that in nucleus you have protons, outer shells have electrons, the charge is balanced always. The electrons which are there in K and L are nothing but closely bound. So if you all are from, like, if someone has a chemistry related background must understand that okay, there are this different energy levels with respect to it. So we aren't much more concerned into the energy levels as of now over here. But okay, so how electrons are placed in those and how far it goes, the energy decreases. The binding energy to the electron to the nucleus decreases, and that's in how it increases. Okay, so how energy increases decreases is like this potential energy to which point it was there, and then later it's moved. So potential energy it's still in that particular place. It's static energy. So indication it's still negative, but that higher. So that's a higher binding energy. Whereas to the far free electrons, it's 0 kilo electron volt. Okay. So in terms of the energy that a electron holds, it's represented by kilo electron volt. Okay. So K kilo electron volt. I hope that you know. Okay. Then the band structure, not at all that important, but okay. We know that for conductors have electrons move very freely through them. It's a conductor, right? So it does not need a gap. So hence there's an overlap in between the valence and conduction band over here. But in case of semiconductor, it's not a case. It's just a mixture of them. And if it's an insulator, it won't allow it to pass. So there's a huge resistance in between them. So hence the band gap is higher. So the energy levels and the band gap go through this way. It's overlapping, so none, or you can consider as zero, higher and higher. Okay. So simple things that you must know so that you will understand okay the nature of your sample. If your sample is not conductive, then you need a coating on top of it. How that coating will help you? It will make your sample conductive enough. If it's conductive, then it will allow electrons to pass through it. Right. Now, same thing that we saw that the inertial electrons will have a lowest energy nearest to the nucleus, whereas the outer shell are the highest energy outermost ones. Conduction are nothing but the shared electrons, and this outer electrons are nothing but they can be fairly detached from the atom. So only a small amount of energy is to be supplied to them. Okay, so this is how the electron band diagram looks, and when as in how the electrons are loosed. Only thing that you should remember is that okay, because of this phenomena, there are different kinds of electrons that would be passing through when your electron beam hits your sample, and now from that particular sample it will knock off some different electrons. Those electrons will give you characteristics of different properties of your sample. Okay, so because of that these things are necessary for you to understand. Now based on the wavelength of electron, the mass of electron, there comes a relationship of the mass of electron, which is nothing but from the theory of relativity. So here the formula is not there. I guess even I can't write, but okay, you can refer it to the lecture slides. The formula goes as okay, you have mass of electron divided by 1 minus V by C and square of it and whole square root of it. So if you just look through, so you see that okay, that comes a term where you relatively correct for it, and as in how your wavelength of the volts increases, the voltage of the source increases, you see that the wavelength also decreases. So that the relationship is nothing but inversely. So you know the Broglie's wavelength, right? So H is lambda is equals to H by B. That's H by NV. So I don't have my tablet today, but just verbally. So we always know that this wavelength and volts are nothing but inversely related to each other. So in a way, we get a relationship in that way. Okay, so that being done, there's again second lecture. Third and fourth are very slightly related, but we'll just see first three lectures, which I know that would be very helpful for you to solve this week's assignment, and that's why I'm stressing on these slides bit more with respect to the other ones. Okay, so you have a source of electrons. Now, why this source? Usually it's thermionic. So thermionic is like the term stands for thermal energy, right? Now, what happens in there is we'll heat the source, so that will extract electrons from it. Those electrons will pass through a sample, right? Now, this here, as in how it's written over here, that electrons are nothing but accelerated across a potential difference in order to generate a beam of electrons, and that beam of electron we can control its energy, we can control its wavelength, right? So if in cases at temperature if it exceeds 2700 Kelvin, then a tungsten wire will emit tons of light and electrons. So in case of light, it's like this. So if you have electron current passing through this way, the electrons will pass the other way. Similarly, you have this tungsten wire quoted over here. A stands for the flow, and this is the resistance that will pass your circuit through. If so it will always need a earthing, right? Where your electrons can go after heating the sample off if there are some abundant of electrons. That's why you always need to have a ground to the supply, right? So this is how usually if you see in a light bulb, it always is placed as an hairpin. Now this hairpin is nothing but what happens to this pin. So if you see this particular band, if you increase or decrease the diameter of this band, it will help you engage more number of electrons or less number of electrons within it. So that will nothing but is termed by this term, that is Wenelt cap. Now what is this cap is it is held at slightly increased or higher negative voltage, so that it will be able to adjust this diameter of the filament or end of the filament, so that you can control the number of electrons that are passing through it. So that way how SEM or TEM works through. So we have knobs to adjust all of these electrons, and how much electron beam we want, okay, how much volt we want a sample to pass through. In some cases, if our sample is not conductive enough, there comes a place where, okay, all our electrons are getting deposited at one point. So that's something which is called as charging of the sample. So we don't want that something like that to be happen. Hence, a proper ground is very necessary for in a particular electron microscope system. Also, when that is provided, we don't want that at a particular time in a particular sample area more or it's like higher number of electrons are getting deposited, hence these numbers are being adjusted in the same manner. Okay, so this cap is nothing but will act as a grid, and hence the gun is nothing but called as a triode gun. So you have a source, you have this part, and you again have a high voltage supply supplying through it. So you can complete it's like adjust these parameters, and hence they can be controlled by the potential difference in between the filament, here this filament and this particular grid that you are passing through. So the diameter is nothing but effectively the size of the electron source. So this diameter will only eventually lead to the size of your electron source gun. Okay, so now you have a chart over here which shows that, okay, as in how when electrons are starting to how do you say, okay, when they are getting emitted from your electron gun, they won't have that much energy, and there are very fewer number of electrons that are passing through it. When a higher number of electron at the point after it saturates that biased current or your threshold current, it will reach your filament current, and after reaching that filament current it will eventually saturate, and hence it won't increase. Now this increases, and this current is eventually function of your temperature. As in how your temperature increases, the number of electrons will pass through it will also increase. Now, you know, number of electrons and the current flowing is nothing but directly proportional to it. So it will eventually tell you the number of electrons that are nothing but pass through your electron beam, through your electron source. So this type of curve is nothing but it's called as an emission curve. So what's the a current that's passing through your system or from the electron source and will eventually govern your number of electrons. Okay. After it, you have brightness. So this brightness is not what you see in your phone that okay, you just increase the brightness so that the amount of light that is coming through will increase. Eventually, this brightness also governs the number of electrons also. So this is nothing but the beam current density. How much current your beam will pass at a particular area in the sample. So this is per solid angle. So at a different cross section. So it just tells you that how many electrons per second can be directed at a given area specimen. That's it. So this will also be governed in the same way by that okay, which type of filament are you trying to use and its function of temperature and the work function of your beam. So as in how this work function decreases or your solid angle decreases, the area or aperture where you're trying to send more number of electrons as and how your temperature increases will also increase. So that is how your brightness increases. Okay, that's very simple. That how your brightness increases. There are some numbers, but no need to remember those numbers. What you need to remember is that how the unit comes along. So you have your current density. What current density is nothing but current with respect in a given area. So that's nothing but ampere per meter square. And now you have per unit solid angle. So solid angles or cross sections are always represented by steradian. So it's steradian inverse. Okay. And these are different kinds of thermionic guns that you have. So it's one such example of a tungsten gun. But nowadays in electron microscopes, you no longer see these kind of guns. However, what we
However,
see
what
is
we see.
okay, someone's trying to say something. Oh, I guess. Okay. So this was also one such example. This is like lanthanum hexaboride. So what happens in this structure is it will provide you a very lesser resolution. It's very expensive. It needs conditions where you need to store it at respect. So it's nothing but a how do you say it has an oxide component to it, so it will get corroded over time, and the resolution that you get through these systems is also lesser with respect to your tungsten based systems. So that is why people have discontinued using this kind of crystals in a day because but one positive point that you can take through this thermionic guns is that it will restrict your electron beam to a confined area, and that will help you reduce those chromatic aberrations that you have. So it will hence reduce those aberrations in a point. So it will reduce the wavelength and the region that you are trying your beam to be simulated in. So it's a in a way it's a ceramic material and hence it's not used in a way now. Okay. So after it came the eventual, it's like the field came to a point that okay, they use this field emission guns. Now, what these field emission guns were, they are also something which are based on tungsten. But here you have, if you provide a material that's high enough electric field, and that electric field should be greater than 10 raised to 9 volt per meter. So there are enough probability or probability is higher enough that electron will leave the surface even if you have not provided that much amount of energy or work function to knock off the electrons from those shells. So that's some phenomenon in quantum mechanics called as tunneling. I exactly don't know what's the difference in between it, but I suppose that it's similar to that okay, you don't give enough energy but the electrons will come off because of this high electric field in the surface. So Here in this case, because of this field emission guns, you don't need to store them at is like colder enough conditions, which is like cold FEG or all, but they will just work on ultra high vacuum technology. So this ultra high vacuum is, the vacuum should be lower than 10 raised to negative 7 pascals. So this is better. Why? Because if you use this thermionic guns, that is nothing but heat the gun and then generate it, it's much more expensive in that way. So hence this is very okayish. So not okayish, but far more better than your conventional ones. Okay. And the diameter of that particular point is like, it's very sharp pointed. So that's 0.1 micron. So it's a very delicate structure. And if anything happens, a number of electron reflects back to that surface also, it will get destroyed in the way. So it will get broken off in that point. So again, oxidation will also break off your tip in that particular manner. So what happens here is, you pass on electrons, the extraction node, and then again to the acceleration node, electron will increase. So in a way, through that cap, that band that we saw over there, will govern the size of the diameter of the number of electrons that will pass through it. Okay. So the advantage of it is also that it will also reduce your beam spread. So it will this if you use the thermionic sources, you have an energy spread of 1 to 2 collect electron volts, only electron volts. But in case of this FEGs, which are like stored in ultra high vacuum, so you have energy spread much more lesser. So if you do this or use this kind of electron guns, you get a very higher spatial resolution, and in a way you'll also get higher brightness. It's not only because that okay, you are using a source under vacuum, so which won't even contaminate or provide any aberrations to your sample, or the beam won't get diffracted enough, but it will give you a clean monochromatic supply of electrons. And that is how you will get off through all the effects that happen, and you won't have to correct for diffraction in a way. So that is how, is like, that's all about different kinds of not different kinds of electron microscopes, but the into it, the cross section and architecture of electron microscopes, the type of tip that we should use, and what happens and how electrons get propagated. So this is how there are different beams, and how the voltage, and this like how people have been conventionally using the tungsten ones. Then we went to lanthanum boride, and then there's this field emission ones. So brightness also increases, the energy spread also decreases. However, your vacuum is higher with respect to them, so it's not that much expensive also. The spread,
Ma'am, excuse me,
yeah,
ma'am. Here I would like to know nowadays they since it is came with that high advanced field emissions,
yes.
so we can consider whatever available that spectroscopy they come out from that which is having low advantage of tungsten and LB lab 6. So
Yes.
nowadays we can consider all it is using field emission, or still there is something that advantage still the peoples are using these two options.
Yeah, nowadays the systems, all systems are field emission. You won't get that much systems with thermionic emissions.
Okay, got it, ma'am. Because is there is anything advantage, or it is only the commercial factor, I mean price factor.
Yes, exactly. Only price factor. And these systems also don't require that high maintenance thing. So, of course, they are high maintenance systems, but with respect to each other, field emission systems are much more easy to be maintained.
Okay, ma'am. Thanks, ma'am. Thank you.
Yeah. They are sensitive with respect to the thermionic ones, but only thing is you need to maintain that much vacuum. If vacuum is not built up enough there, your electrons won't be able to propagate or pass it through. So as we say, that sound needs a medium to travel. Here, electrons don't. So electrons will be able to pass through the vacuum, and hence we need that highly tight vacuum to be built up there. But it's eventually lesser than this thermionic system. So hence it's better in a way that okay, we use those. Always the differences in between which kind of tip that you are trying to use. So here in this case, the tip also, only thing is over time, if your tip gets oxidized, will get broken, so you need to replace it. So that is nothing but will cost you double the price of the system that you have bought at first.
But this high vacuum is achievable, ma'am. This much torque, 10 to the power minus 10.
Hmm.
It's practically achievable or it is theoretically
No, 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 it's achievable. So the systems that we
achievable?
also have, we build vacuum till 10 raised to negative 7 in there, pascals.
Okay.
Yeah. Okay, so the next lecture, according to me, is fine that okay, they are just following on through the previous lecture. So you know that okay, we have a left hand rule, how current flows in the direction of force. You just take it, you'll be able to know through this. So these are like basics in class 11th and 12th. Um, how the lens works, scanning coils. So taking this all in, I think that we can directly go to the assignment, because I think for this week's you don't need much more information apart from that. If we need, we'll come back to these points and revise them again. Okay. So do you have any questions from the first three lectures till now?
Ma'am, you have mentioned it is 11th plus 12th syllabus. That means it is covered in 11th and 12th physics, ma'am. You mean?
Yes, yes. Sorry, yeah. Physics.
We are completed very long back. That's what we don't. Okay, ma'am.
Yeah. So
Okay.
we'll cover them as in how the assignment
Mm.
needs us. So we won't go through it if it's like too much detail into it. That's why.
Okay.
Okay.
Okay. Okay.
So let's start the assignment for this week. Uh, so since I don't have my tablet, I've made that okay, we'll get all the explanation in the slides that's provided to you. Okay. So auger and secondary electrons are primarily generated from 2 minutes. 2 minutes. 2 minutes. I guess my net's not stable enough.
Ma'am, is there is any technical issues or we are, or we are not audible to you, ma'am?
Yeah, sorry. I guess my net was glitchy. I hope you are able to see my slides now.
Yes, we are saying, ma'am.
Yeah, I guess the display is not working or something. Like screen subtitles. I don't want this presenter view, but this presenter view comes coming up. Let's see. Okay, there we go. So, first question. I hope slides are going. Huh, yeah. That ovary and secondary electrons, they are primarily generated from. You all can take like 5 seconds, a brief stop, and then let me know which answer you think is correct for the same. So we can answer this question that okay, where are these electrons actually? So they towards the near shells? Are they in the farther shells? So what happens? Where are they generated from? If they'll get that knocked off, then which where in the system will they get affected? Anyone? Okay, so the answer for the same is here. Surface of the
Surface of the
specimen.
specimen.
Yes. So why surface? Because these are nothing but, I guess, screeners. Yeah. So these are generated throughout the interaction volume. And what happens is they are nothing but lower energy electrons. So these are in the far away shell. So they can escape and get knocked off very easily with respect to this backscattered electrons. Elsewhere, they are observed into it. Hence, they are nothing but they are generated close to the surface of the specimens. Hence, they can be detected. Okay. So, explanations also this week I've written all of them in the slides so that you can see them through. So, determine the wavelength of an electron microscope that's working at 200 kilovolts. So, for this, you'll eventually need to calculate if you can calculate the free field too, or else I can show you the calculations right here. So if you have an operating voltage of 200 kilovolts, you have wavelength relationship from the de Broglie wavelength. This is nothing but without the relativistic correction. So here I have not, for this I've just done the calculation so that my answer came out to be this one. The assignments also show this one, but you can cross check if correcting the relativistic correction you get a different answer or not. I think that only in the significant digits it will change and won't affect the exact values enough. So having only three significant digits with it. So you compute the electron voltage, multiply the electron energy, one charge times your operating voltage, and you get the wavelength. Inverse of it, you get like this nanometers of wavelengths. Okay. So probably only in this significant digits the correction factor will affect it. And again, the question also says that neglect the corrections, but better if you do it both ways. Okay. Then next, an electron beam when focused on the surface of sample, what can happen to it? Will it penetrate through if the sample is thin? Will it scatter if it's thick? Okay.
Your screens are different than that of what you are speaking.
Oh, I guess the screen is this one, no? I can see in my second display the screen is correct. I'll
Okay.
just stop sharing and reshare if that works for you. Mm.
Yeah, not okay, ma'am. Not okay.
This is working?
Yeah, yeah.
Okay. So what will happen to the electron beam when it's focused on the surface of sample? So will it scatter? Will it penetrate? Or again scatter if it's thick? Or will it scatter if it's thick and penetrate if it's thinner? What happens to the beam? Anyone? Okay, so the answer for this is that it will scatter if your sample is thick and will penetrate if the sample is thin. Okay, let me just take up a pointer here. So the answer for the same is this B. Okay, so how and what happens? Because it will penetrate because of this high energy electrons, and in the absence of these high energy electrons in the direct path, if your sample is thicker, then it will get scattered numerous times and eventually will get absorbed. But if it's thinner, then it will penetrate it and will come back to you. So hence the volume remains larger than the sample thickness. So it will penetrate through and through, otherwise will get absorbed. So hence for thinner samples, it will scatter back. For thicker samples, it will penetrate, will eventually get absorbed. Okay. So we do Monte Carlo simulations. We haven't talked about it yet, but I guess through general understanding, they are primarily described for the electron which are interacting with the specimen. So, what part of it we actually think over there? So, why do we do these simulations? We do it for the electron trajectories. Why? Because this points as scattering angle. That's up to us. That's user defined. Elemental trace that's present in the specimen. The specimen is yours, so you should know what elemental trace it has. So because you are making the specimen, you just want to know that what will happen after characterizing through it. And this type of microscopy is only imaging, so you know that what actually is in it, so you can help the user provide these components into it. Mass thickness, you know about it, but the trajectories of electron, how it passes, how it goes through, how it's interacting with your specimen, is how we monitor in the simulations. Okay. Then scanning electron microscopy works on which method? Does it work on transmission, scanning, diffraction, or absorption? Well, this is easy one. You can answer this. Just a random guess is also fine. So what happens in a scanning electron microscopy? The name says it all. Anyone? Okay. So, I guess. So that depends on a scanning method. We are nothing but raster scanning our specimen, and the beam will go through them point by point, and we'll just get electron back to scattered electron back, and we'll image them through that. We'll see that, okay, how the specimen is, how the structure of specimen is wherever the beam is focusing at. Between backscattered electron and secondary electron images, what actually happens? Which one has a so does do we say that backscatter electrons have lower spatial resolution than the secondary electron images, or both share similar resolution, or the backscatter ones have a higher resolution than the other one? Which one? So you know that from where the secondary electrons come. Do they come from the surface or from depth? Or the backscattered electrons, do they come from surface or from depth? If you know the answer for this, you know the answer for this question. Okay, mm, you can try answering it.
Option A.
Yeah, option A, because this backscattered electrons are nothing but are from depth, so they'll what energy they'll have is also lesser, so hence the resolution would be lesser. But it will tell you information about the structure in depth with respect to the secondary electrons which are generated from this near to the surface. Okay. If we increase the charge of a nucleus, that will influence the elastic interactions with an incoming electrons. How what happens? Do we increase or decrease the scattering angle, or if decreasing the intensity of the beam, or there's no relation between all of them? So increasing charge of the nucleus, that means more electrons. You'll have an elastic interaction, more interactions in between them, and not that much
And B.
inelastic very G's, sorry.
A scattering angle would increase.
So scattering angle will increase. Yeah. So what happens is if your angle increases, the force that's generated will also result into a greater deflection and hence the larger scattering, hence the energy, the charge, everything will increase in that way. Okay. Which parameter or combination of parameters best indicates the probability of electron scattering? So we just saw now what happens, that do we have the interaction of the cross section and the mass thickness, or it's it because of the path length through which it's passing through the sample thickness, or the path length and the cross section interaction, or it's only the interaction cross section? Okay. So the answer is the path length
See,
as well as the interaction
main
cross.
free path and interaction cross section.
Yes. So
Right?
the mean free
Right.
path length and the interaction cross section. So why? Because your cross section is nothing but the area where your scattering will happen. And if it's divided by the actual area, you get the mean path length through which your sample is getting passed in between multiple scattering events. So that is how both are nothing but important to tell you that okay, what or till what extent your scattering will happen, and that's a success phenomenon. Okay. So hence your probability will higher in that case. So choose the correct statement. So this is for the secondary electrons and the backscattered electrons. What happens if they are emitted from the surface with lesser than this energy? Are they classified as secondary or backscattered, or lesser than 50? And which ones? Okay. Emitted from the surface, emitted from the surface. Hmm. Okay. Which one do you think? I guess we also saw numbers when we were looking at the microscope and the electron, this diagram. So we see that this the energy when it's lesser than 50 electron volts, they are classified as secondary electrons. There's no way that okay it would be backscattered electron in any of the cases. Why? Because these are nothing but from the in depth. So for those kind of electrons to be generated, you'll have to send a very much higher energy from your source so that it interacts with the specimen, and hence those electrons will even have that lesser energy when they come emitted back. So not 50 electron volt, that is nothing but only for secondary electrons. Okay, so these are like outer shell electrons will get emitted fastly and hence will have an energy, kinetic energy less than 50 electron volt. Okay, so what function do the outermost shell or this valence electrons serve in electron microscopy? They don't have any involvement. Well, that's okay. It will generate the detecting signals or will produce electrons from the electron gun. What happens?
Option B, produce electron from the electron gun.
Exactly. Because now these electrons are only means for us to be involved in electron microscopy. So A and D are like completely cancelled out, and you have generating detection signals. So for detection you have something else. They only help you produce electrons from the electron gun. Okay, and hence eventually a current would be generated. So the secondary the scanning electron microscope provides information about which type of features in your specimen. Will they tell you something about your chemical composition or defects
Option
topography
A,
features?
topographic features, surface characteristics.
Yeah, so it tells you about everything because you have EDS there. You can do elemental analysis. Through that elemental analysis, you can get information about the chemical composition. If your sample has cracks, or if your sample is like fibers or an hydrogel, some scaffold or something, you'll get to know that if there are defects in your specimen. And of course, you get information about the surface features. So that's all of the above. Okay. In a secondary electron microscope, the captured image is what? Is it a real and grayscale because you do see grayscale, or is it a reconstituted grayscale? It's a real one, of course, we know, but is it a real and a color? Well, you can't always see it real one. If you say real one, mathematics people will come in and will say that, okay, you have complex components in here. How do you say real? So, which one?
Option A, reconstituted grayscale.
Yes, exactly. So it's reconstituted. So after passing it through the detectors, there's some image processing, and that is how you see it as the grayscale on your display screen. Well, it's actually not. Okay. How does a heavily charged nucleus influence the angular distribution of the scattered electron in elastic interaction with an atom? So when you have elastic interaction, how does angular distribution of the electrons will affect? So do they depend on it, or lower or higher scattering, or will exhibit an exponential dependence on the scattering angle? So I guess there was a term from the same. So but okay. So if you look for this
Higher
question,
higher scattering angle.
yeah,
As the
exactly.
atomic number increases, scattering angle would also increase.
Increased, exactly. So if you have elastic scattering, as how someone answered just now, scattering will also increase, number of electrons will also increase, no energy is transferred from back to back without getting any interaction back. Okay. So which one is a real concept and can be observed in an electron microscope? So is it a scattering angle that you observe, or a cross section, interaction volume, or mean free path? What do you see when you image? Where do you see?
Interaction cross section,
You see
that
in a
would be different.
volume. Yeah.
Okay, okay.
Yes.
So
So interaction.
interaction cross section is same as differential cross section. No, right? No,
Yeah.
something
Exactly.
different.
Yes, I guess you understood. So, why this interaction volume? This is a volume which is generated after your specimen and electron are getting interacted. So, you can assume this part as that of depth of field of your optical microscope imaging. And hence, the shape and size of this particular volume will determine the type of scattering that's happening in there. However, your interaction cross section is a step that's coming just in front of it, of the first step, after which your volume is getting generated. Okay. So, last question. Which material composition is commonly used for this cold cathode emitters in field emission electron microscopes, scanning electron microscopes? Is it so? We know that it's tungsten, but is it coated with something else, or which type of tip it has? So probably it will depend from per system to system or manufacturing to manufacturers, but they are usually tungsten ones and they have a pointed sharp tip which is like zero point 0.1 microns in dia. So that we saw in the slides, hence the answer for this is this one. Okay. So if you have any further questions, you can let me know, or else we are done for the day. And thanks for joining for this Sunday. Any questions?
Um, just my network issues, I not able to continue that. Just to show the question from 1 to 15, ma'am, because I'm recording that one, so I will refer with that.
So these sessions are being recorded, so you can go to YouTube and see them if you want.
Okay, okay.
Yeah. So no need to just use up your space. Mhm. Okay, so if you don't have any further questions, thanks for joining. We'll meet
Ma'am,
next week. Yeah.
one question which I had was in the class, it was told that the interaction volume um, direct measurement of interaction volume is not possible. That was
Mm.
something which was mentioned, but in that question here in the MCQ,
Mm.
uh, the answer was interaction volume. It's a real
Mm.
concept. Okay. It's not
Mm.
talking about whether measurable or not, right? Okay.
Mm. Mm. Yeah,
Okay, ma'am.
exactly.
Nothing.
Yes.
Thank you.
Thank you. Okay, so thanks for joining then. Those who have questions can stay back and ask me. I'll be here for like next 10 minutes till 6 o'clock, I guess. Thanks. Okay. Do you guys have any questions? Okay. So if not, then I guess let's end this session over here. We'll meet this Saturday, 5 to 7. Okay. Thanks. Bye. Happy weekend.
Thank you, ma'am.
Thank you.